let's continue our talk on dispersion forces. So while we said that everything has dispersion forces, some things have more or stronger dispersion forces than other things. And so in general, larger atoms are more polarizable than smaller ones. And since the dispersion forces come from this polarizability, they have stronger London dispersion forces. So let's take a bit deeper look into that, right? So we have this big atom here with its electrons, and then we have this kind of much smaller atom with its electrons, right? And so let's see why one is more polarizable than the other. Well, think about what's keeping the electrons on this atom. It's that positively charged nucleus. Well, these electrons are further away, and so it's easier to push the electrons around and polarize the atom. And so sometimes you'll hear these being referred to as soft. So soft and easily polarizable are pretty much the same thing. Whereas this small atom, these electrons are very close to the nucleus. Right? And so they're actually hard to push around / polarize. And so they'll have less London dispersion forces. And so these are known as hard, or they're harder than the other ones. And so if we think about what intermolecular forces in general are doing, they're keeping the solid or the liquid together. So if we have stronger intermolecular forces, then we're going to have higher boiling points and higher melting points, right? It's going to be much harder to break apart these molecules, right? Because it's going to require more energy to break the IMFs. And we need to break the IMFs to turn it into a gas. So this picture does a good representation of this, right? We see as we go down the periodic table, here's a list of the noble gases, helium, neon, all the way down to xenon. We see that we get bigger, 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 bigger. And we see when we get bigger, the boiling point increases further and further, right? So bigger something is, more London dispersion forces, more or higher boiling point. So think about SiH4, SnH4, GeH4, and CH4. Go ahead and place in order of increasing boiling point. So go ahead, pause the video, use the knowledge you just learned, and place them in order of increasing boiling point. All right, so hopefully you paused the video, figured this out. Let's check your knowledge. So if we take a look at the hydrogen part is all the same. So really what we're looking at is the difference between silicon, tin, germanium, and carbon. And if we take a look at these, they're all in the same group, right? Here's carbon, silicon, germanium, and tin. And as we just learned, when we go down the periodic table, we get bigger. And as we get bigger, we get more London dispersion forces, stronger intermolecular forces, higher boiling points, melting points, right? So it goes CH4, the smallest one, followed by silicon, germanium, and then tin. And then this picture just shows you kind of the same thing. All right, you can see here in the carbon family, as we get bigger and bigger and bigger, as the period increases, our temperature boiling point increases further and further and further. Little fun fact, real world application, you don't really have to know this, but using this property, this is partially why Teflon works. So if you think about what Teflon is, right, it's that non-stick coating people put on pans and all kinds of other things. And of course, the main property that people are interested in is the non-stickiness of it, right? So if you look at the molecular structure of Teflon, what you'll see here is that it's basically chains of carbon, and they're perfluorinated, right? So they've got fluorines connected all over them, right? If you take a look at this picture, you'll see all kinds of fluorines attached to this compound. And so if you think about where fluorine is on the periodic table, it's on the top right, so it's very small. And so it has very weak London dispersion forces, and so it doesn't like to stick to other things. So that's partially why Teflon works the way it does.